Everyone managed to make a picture of me? Okay, let's start. Actually, I don't need this mask. Oh, sorry. So I dropped it off. My name is Nikita Lipsky, and today we will talk about JIT versus AOT. What a boring slide. That slide is much better. So meet for JIT team is Freddy Krueger, and for AOT team is Jason Voorhees from Friday 13. You know, all compilers are monsters. And every epic story should begin with once upon a time when C++ was cool and new, all compilers were static. C++ was compiled statically, Pascal was compiled statically, and even Fortran was compiled statically. Until into this world came Java. Sound? Okay, there were no sound. Okay, if we talk about Java, we implicitly mean a JVM and a Java bytecode that is executed on that JVM. And JVM can execute bytecode in two ways. It can interpret it, that is slow, or it can compile it down to machine code that will run directly on underlying hardware. But there are also two moments in time when that native code compilation can occur. Dynamic or just-in-time compilation occurs before program launched, and static or ahead-of-time compilation occurs. Dynamic occurs at runtime, and static occurs before program is executed. Please refer to the next slide. Here, above of the dotted lines, you can see what happens before program execution, and underneath of the dotted lines, what happened at application runtime. On the left, you can see a conventional JVM such as an Oracle hotspot. What happens there? Your source files are translated into class files with the help of Java-C, and then they are put into jar files. At runtime, classes from jar files are loaded by the JVM, and firstly, they are interpreted, and with the help of profiler, it is detected a hot code that is fed to JIT compiler that produces native code that runs directly on underlying hardware. In the middle, you can see JVM with the head-of-time compiler. As you can see, all your class files are translated into machine code before program execution, so your application starts on underlying hardware right from the start. In more general case, however, there can be some classes that are not known before program execution. It can be some third-party plugins, dynamic proxies, and so on. So even a JVM with the head-of-time compiler should be equipped with a just-in-time compiler or interpreter to handle such cases. So what we are going to talk today. First, I would like to dispel common myths around Java ahead-of-time compilation. Then we will talk about what challenges it actually has. And then we will talk about all dispute whether static or dynamic compilation is better for performance. And finally, we'll talk about application of JIT and AOT in various fields of use of Java, such as client-side, server-side, embedded IoT, and mobile. But first, let me introduce myself. I have been working on Excelsior JET project. It's a JVM with a head-of-time compiler. It's complete Java-C implementation past GCK test suite. And I worked on this project from the day one and contributed to all its components. On this slide, you can see Java-compatible sign. Actually, we sweated blood to get this sign. Some microsystems before and Oracle now do not give this sign to everybody. This sign in particular means that our implementation is Java-C compatible. So static compilation is possible of Java application is possible in full conformance with Java-C specification. On the next slide, this slide proves that Java static compilation can be needed. It is our customers, only a few of them. Since inception of Java, numerous myths have been developed around Java ahead of time compilation. And I would like to start my presentation with dispelling those myths. And the first myth is Java is too dynamic. It has two features like reflection, dynamic class loading that make Java static compilation impossible by its nature. But let's look closer at those features. What is essentially the reflection? It is some metadata about your program. Class names, field names, method names. Nothing prevents static compiler to just put that data into data section of resulting executable to let runtime routines to use it to enable the reflection. So reflection just works for statically compiled work, static compiled apps. Well, as to dynamic class loading, yes, a completely new class can appear at application execution. It can be downloaded from internet, generated by a framework. But I would like to point your attention to the fact that 99.9% of your classes are usually known before program execution. So nothing prevents you from compiling those 99.9% of classes statically and let remaining 1/10% of classes to be handled by dynamic compiler. So dynamic class loading does not prevent you from compiling majority of your application, absolute majority of your application classes statically. The next myth is Java, AOT, kills the main Java principle, WORA, write once, run anywhere. But listen, this principle sounds like write once. It does not sound like build once. It means that you can write your application once, build it for every target platform, and run it anywhere. Moreover, many desktop vendors already distribute their application in platform-specific installer packages. And for those vendors, adding a static compiler is just an additional step in their build process. And if you're on a server side and use Docker, for instance, please note that Docker image is platform-specific as well. And the next myth sounds as if Java had a static compiler, it would transform it to a sort of C++. That is, if I have a 100 kilobyte jar file, I can compile it at 100 kilobyte executable that I can send to my friend that can run it without having to install any Java. Okay, but Java comes with thousands of platform classes that any Java application can use. How they will appear on my friend's PC? I know what about garbage collection, reflection. But I would like to say, both Java and C have runtimes. But C runtime can only allocate and deallocate memory manually, and its standard library is very small, like stdlib and stdu. Java has way more features, and its runtime much, much bigger. But anyway, using static compiler, you can compile your application classes along with needed platform classes and needed runtime support, such as GC, into one executable, but that executable won't be small. But it can be smaller than the whole Java runtime because static compiler can compile not all of your application classes or of platform classes, but only those that are actually needed by your application. It can help to reduce the resulting size of installer in a great extent. Previously, I have been trying to convince you that Java's dynamic class loading does not constitute any problems to static compilers. If I succeeded, congratulations, I have cheated on you. Actually, there is one feature in Java that causes a big headache to Java static compiler writers. I'm talking about custom class loading. In your application, you can create at any moment your own class loader that will override standard class loading logic. So class reference resolution in your application will function as you define. Why custom class loaders are used today? They are used in Java EE, where multiple web applications can be deployed into one web server, and to isolate them, they are loaded by separate class loaders. And they are used in dependency management frameworks such as OSGI. So with all those modern frameworks, there are entire clusters of Java applications that have majority of their classes known before execution, but unfortunately, all that classes are loaded by some custom class loaders. So how can we compile such applications statically? A compiler has no way to know how to resolve references in such applications. And first, it can give up to resolve references and compile each class in isolation from others. It would work, but won't good for performance, because to make your application work fast, a compiler should resolve references between classes to enable inline substitution between them. But fortunately, there is another solution, albeit partial. Actually, developers do not write their own class loaders. By the way, how many of you have ever written your own class loader? OK. But usually developers don't write their own class loaders. They use ready-made frameworks that employ custom class loading logic internally. Thus, we can learn how class loaders work on those most popular frameworks and support them at the JVM level, as if they were standard class loaders. And I'm going to show how to do that. Let's say we have an application that has majority of its classes known before execution, but unfortunately, all those classes are loaded by some custom class loaders. And first, a static compiler should recognize how many and what type of class loaders will be created at runtime. How can that be done? Any suggestions? By inspecting the structure of application. For instance, if we deal with Eclipse RCP, where each OSGI bundle is loaded by its own class loader, we can scan the plugins folder to learn how many class loaders will be created at runtime. And then we should give a name to each class loader, because it is known that several classes with the same fully qualified name can be loaded into one JVM, provided that all of them are loaded by separate class loaders. So in order to differentiate such classes, we need to add, say, a prefix to its class name with some static class loader unique identifier. How can we name class loaders? If we deal with Eclipse RCP, we can choose a plugin name for class loader name, which is unique in Eclipse RCP. And after we named class loaders, we should distribute application classes among the class loaders. And after that, we can resolve references both within each class loader and across class loaders' boundaries. But as you can imagine, compilation is just a half of the battle. We also need to load compiled classes somehow at runtime. How can we do that? Let's say that at a certain moment, a certain class loader wants to load a certain class with a certain name. Sooner or later, it will inform about its desire the JVM, because class loaders cannot load classes themselves. They can only look up classes, delegate class loader requests to other class loaders, and ask the JVM to load class it has just found. And at that moment, drawing on our knowledge how a particular class loader works, we should derive that static unique identifier from a runtime instance of the class loader. How can we do that? If we deal with Eclipse RCP again, we can find where we named our class loaders with plugin names. We can find that plugin name in an instance field of class loader instance. And then, if we have class loader name and class name, we can find statically compiled class in the executable and load it. But please note that loading of statically compiled classes differs from loading them in a classical JVM, because all that we need to do to load statically compiled class is to create Java lang class instance and fill it with reflection information. All bytecode verification class resolution was performed ahead of time, and code will be loaded by operating system. Talking about practical application of the theory, I can say that we support at Excelsior JET supports Tomcat and Eclipse RCP class loaders. So yes, you can compile your Tomcat web applications with all frameworks that you can use, such as Hibernate, Spring, into executable. And yes, you can compile Eclipse IDE statically as well. So we can claim that for every Java application that has its majority of its classes and respective class loaders known before execution, we can build a static compiler that will effectively transform that application down to native binary. So is a static compilation of Java applications possible? Yes, for sure. Okay. So Java static compilation is possible. But why do you need it? How it can be useful? Let's start from the obvious things. It is known that Java bytecode can be easily reverse engineered with the help of decompilers. Decompilers are free, easy to use, and produce amazingly readable source code, almost the same as original. So if you do not want to distribute your application in almost source code form, you would use a tool that would hinder reverse engineering process. And to-go solution is obfuscator, and its simplest form, name obfuscation. Name obfuscator replaces all class method field names with nonsense, so a resulting decompiler output is much harder to read. But name obfuscation has one big drawback. If you use reflection, or a framework that you use reflection, you should supply your obfuscator an exclude list telling it not to change class field method names that are accessed via reflection. It is time-consuming task, prone to errors. Moreover, what you would like to do with your application in the future? The more probably you will refactor it, renaming your class field method name, and then you should renew your exclude list. If you forget to do that, everything can work on your development PC, but when you deploy it to end customers, everything can stop working at the most inappropriate moment, and you will not see what happens at first sight. So why static compilation is better here? First, there are none of tools that can produce Java source code from native code. All that you can do with native code is to disassemble it. But to read and understand disassembly require from you much more qualifications than to read and understand Java source code. Moreover, it is much harder to understand what the code does when no symbolic information is attached to it. And after all that optimizing transformations, all that inline substitution specializations that can be applied by static compiler, the resulting native code can only remotely resemble the original. Simply put, static compiler protects your Java application from reverse engineering to the same degree if it were written in C++ at the first place. Next comes the opinion that statically compiled Java application should start faster than running on a conventional JVM, because there is no warm-up cycle involving interpretation, profiling, and dynamic compilation. Is that true? First, you probably noted that large applications restarts much faster than they start for the first time. It is true for any application, whether it's written in C, C++, or Java. It so happens because when an application starts for the first time, a lot of code and data should be loaded from the hard drive. On the subsequent runs, all that code and data is already in disk caches, so your application starts much faster. Now, can static compiler improve startup time? Please note that native code is thicker than Java bytecode. due to its low-level nature. For instance, fetching an array element is a single instruction in Java bytecode, while expressing the same semantic in native code will produce multiple instructions. So native binary produced by a static compiler can be significantly bigger than the original jar file. Now recall that the most of the time during startup is spent in loading of code and data from the disk. So everything that we won eliminating the warm-up cycle, we lose because we need to load more code and data from the hard drive. And when we did our static compiler for the first time, it was a real surprise for us that startup time improvements are not so significant as we expected. But we solved that problem. We do application startup profiling that is easy to automate. And during startup profiling, we identify code that is executed on startup. And then we place that startup segment into the beginning of the executable and preload it with sequential reading that is much faster than random reading on a rotating media. And as a result, Java applications start really fast. On this slide, you can see startup times of 3 applications of similar functionality. All they are RSS readers. First 2 applications are native Windows applications written in Delphi and C++. And third one is a Java application. Third group of bars presents startup time of Java application running on conventional JVM, while the fourth group of bars presents startup time of the same Java application running statically compiled. As you can see, statically compiled application runs as fast as their, almost as fast as their native analogs, while the same Java application running on conventional JVM start 2 to 3 times longer. So static compilation clearly helped this application to start natively fast. Next, let us consider the performance. There are 2 opposite myths regarding performance in JIT versus AOT battle. And first myth is, by compiling Java statically, we are making it equivalent to C. C is faster than Java. Hence, statically compiled Java is always faster. So what is incorrect in this statement? Any guess? Actually, everything is incorrect in this statement. Really, Java, unlike to C or C++, is managed language. What does it mean in practice? That when you dereference a null pointer or violate array bounds range, you will get null pointer exception or array index out of bounds exceptions that you can catch. In C, you will get immediately sigfold without any opportunity to recover. But this or that safety features of Java do not come for free. And they are not free both for static and dynamic compilers. So Java has some inherent overheads impacting performance that are absent in C. But the statement that C is faster than Java is also incorrect. For instance, if you write an application in C, you will likely use some native libraries, and not all C compilers can use the code of that native libraries to optimize your application. On the other hand, all Java library code is available both for static and dynamic compilers. So even standard code from Strat classes can be inlined into your Java application code, giving your application a significant performance boost. But there is also an opposite myth. Effective optimization of a Java application is only possible in the presence of its dynamic execution profile. This myth is the most difficult to bust because the best JVM engineers have been hammering this myth to Java developers' heads for years. But I would like to bust it anyway. So if we are talking about performance, we are talking about code optimizations. It is not enough to just compile your application to native code. To make your application perform fast, your code should be passed through numerous optimizing transformations. On this slide, you can see only a few optimizations that can be applied to your code. Please don't read this slide. Discussing all that optimizations is far beyond the scope of this presentation. But I will tell you very briefly about optimizations that are especially critical for Java. So what we have in Java? It is common in Java to write applications in very good object-oriented style, using various design patterns, frameworks, best practices. So from a place when you need some functionality to a place where that functionality is actually implemented, a control is passed through a long chain of intermediate calls. So a good optimizing compiler should see that chain and inline it all to the caller method. But all calls in Java are virtual by default. So methods called devirtualizations becomes a very critical optimization for Java. And method called devirtualization can be based on the following three techniques. It can be based on class hierarchy analysis, type inference analysis, and profile-guided optimizations. Let's consider them. The idea of class hierarchy analysis, or CHA, is very simple. We traverse class hierarchy to take note of the methods that are not overridden. It means that we can call them directly. And dynamic compilers can even inline such methods unconditionally. However, this technique has one drawback. When a new class gets loaded that overrides such a method, it immediately validates all its inline substitutions. So a dynamic compiler should throw away all affected code, de-optimize it, recompile it, so on. In the static compilers, we cannot do that. Instead, we insert a check that checks that a receiver type, runtime type of a receiver object was the subject of CHA. And if the check passes, we execute inline body of method foo. Else, we just call that method virtually. Please note that this check can be performed very efficiently with just a few native instructions. But anyway, CHA has disadvantages both for has overheads both for dynamic and static compilers. But fortunately, there is another technique that often allows us to devirtualize always, unconditionally. It is based on the fact that we can call all methods of newly created object directly, if we recognize such a pattern. Is it clear that we can call method directly in such a coded pattern? Because we statically know exact class and exact target method of that call. Okay, the idea of type inference analysis is to calculate instances of what classes are assigned to a local variable A. And if it appears that all possible sources of such assignments are new operators on a known set of classes and method foo is the same in all those classes, we can then call method foo directly. But a code pattern when we assign to a local variable only new operators are not very frequent. More often, we would have values that are returns from some other methods. So how can we devirtualize subsequent call in that case? Please, let's imagine that method bar always returns instances of class B, and method bus always returns instances of class C. And in that case, we can call method foo non-virtually again. But this poses the question. How do we know what methods bar and bus return? And here we can enjoy something that none of dynamic compilers can even dream of. A static compiler can use, within reason, as much time and memory to optimize your application as it needs. For instance, it can scan all methods of your application prior to optimizations and calculate some useful information about each. For instance, it calculates instances of what classes are returned from concrete methods. And starting our analysis from the list methods that do not call anything up to call hierarchy, we can calculate such information quite efficiently. And the situation when we know what bar and bus return often become available. The analysis that scans all methods of your program called global analysis. And what else it can be used for? How about detecting whether an argument of a method does not escape to a shared memory? It then can be used in escape analysis that determines whether a locally created object escapes from the method's stack frame into a shared memory. And if it appears that it doesn't escape, we can allocate such an object on a stack rather than a heap. But local escape analysis cannot detect such objects if they are passed as parameters to other methods. Probably you know that HotSpot does escape allocation, optimization. But in order to do that, it should inline all methods that, to which subject for stack allocation is passed. But it is not always possible to inline such methods. Hopefully, with the help of global analysis, it is not needed to inline all such methods because we know if a method parameter does not escape into shared memory or not. And I am going to show how it all works together. Let's say we have a pretty freaking code pattern. Iteration over a collection. JavaC compiler will actually desugar this into the following code. We get iterator from the collection, and with the help of hasNext and next methods, iterate over a collection. So how can we optimize such a frequent code pattern? Please note that hasNext and next methods are abstract, so we know nothing about them in general case. But what if we have some bits of information from global analysis? Let's say global analysis has shown us that getCollection returns always returns instances of array list. And things suddenly becomes much better because we know everything about array list. And if we inline its iterator method, we can see that iterator becomes not an abstract iterator, but a concrete iterator. And we know everything about this iterator. For instance, we know that in its hasNext and next methods, iterator object does not escape. So we can allocate it on a stack. And if we inline its constructor, we can see iterator fields. Then if we inline hasNext and next methods, we will see that iterator object is not used as iterator anymore. It is used as a set of fields. So we can translate them into local method variables. And what we see now? We see that it's a simple for loop with a counter. Its inductive variable was an instance field of unknown object before optimization, and now it can be allocated on a register. The loop can be versioned. All runtime checks can be removed from a fast version. We can inline do something, move out of the loop all its loop invariants, and finally we will get the most effective code for this quite frequent code pattern. And I would like to emphasize that we did all that amazing tricks basing on our optimization only on a static analysis, without executing that code any single time. So, concluding my speech about optimization, I would like to say that program analysis, optimization, and respective internal representation can be quite sophisticated and require a lot of computational resources. And as you have just seen, that some optimization can give opportunity to other optimizations. So it is not enough to perform optimization only once. Ideally, we should repeat them until reaching a fixed point. And the global analysis depends on the whole program. So a volume of information it produces depends linearly on the size of your program. So in our static compiler, we store the results of global analysis on the hard drive because it does not fit to RAM. So the final question is, can JIT compiler afford all of that? It shares CPU and time and memory with your application. And if these first two points are arguable, I can say for sure that global analysis is not for dynamic compilers. Really, can you imagine that a dynamic compiler will use gigabytes of hard drive space to perform optimizations at runtime? But what JIT compilers are good for? First, they can compile not all methods of your program, but only those that are actually executed, and executed frequently enough. And it is actually the main advantage of dynamic compilers, because they can spend much less computational resources as a result. It's the main advantage because from our experiments we performed several times, profile-guided optimizations do not give so much performance, but it's enough to compile hundreds less of classes to achieve acceptable level of performance. And this observation makes dynamic compilation at all possible. Then dynamic compilers can do devirtualizations basing not on a static analysis, but on an actual execution profile. So if a dynamic compiler sees that a particular call site, the target method was always the same, it can assume that it will be the same the next time and in the future and inline it. Extrapolating the technique, a dynamic compiler can see hot execution traces in your program, row them in basic blocks, and optimize them very aggressively. And it works and works very well. But what happens when an application does not have an evident hot code? It often holds, for instance, for UI-centric application, when you have many code for menus, windows, event handlers, and so on. But that code is not executed frequently enough to justify JIT compilation. So that code simply interpreted on a classical JVM. And it, of course, influences user perception of your application. So, for instance, if we present the same applications running on conventional JVM and statically compiled UI application to a user, he won't notice a difference at first sight, but after working in the application for some time, he will see that statically compiled app performs a response to his input faster. The difference can be demonstrated on the following benchmark called JFCMark. We created it 0 years ago to measure UI responsiveness. The benchmark takes standard swing set to demo from JDK and manipulate it with the help of robot. Open, closes windows, model dial, etc. Scrolls down rich text, control, etc. And the benchmark has two modes. Short run, when you just start your application, and long run, when you use it for some time. And here, the performance of Excelsior, JET, HotSpot client, HotSpot server is compared. And as you can see, during short run, statically compiled benchmark runs 2 times faster than HotSpot client. In a long run, HotSpot's client becomes faster, but it is still 1.5 slower than statically compiled benchmark. But you may say, OK, who writes client-side software nowadays? All we have is server-side, and on the server-side, dynamic approach works better, of course. OK, but I would like to ask you, can a static compiler use a dynamic execution profile as input? And the answer is yes, of course. Actually, all modern C++ compilers implement profile-guided optimizations. But it can be not so convenient for UI application to gather execution profile anytime you need to rebuild your application. But as you remember, everything is more or less good for UI applications, even for statically compiling UI applications in the without profile. But if we move to the server side, we can see that after working on the high load of generated by real users for some time, an execution profile will likely stabilize. No new classes get loaded, and the JIT compiler sits idle. So what if we now send gathered profile to another server, where static compiler installed, and won't having relaxed memory and time constraints, and an actual execution profile? It can optimize your application in the most effective way. And I think this is exactly the scenario where static compilers can be beneficial on the server side as well. Moreover, we at Excelsior already have some satisfied customers at server side. Some of them benefit that performance of statically compiled is much more stable because there is no de-optimizations that can occur at known time, so latency becomes much more predictable. Some of them benefit better that statically compiled servers starts faster, 2-3 times faster. That can be important when you need to launch a bunch of microservices simultaneously. And when a server starts, it performs the same as other in the cluster, so load balancing does not suffer from this. Let's now take a brief look to the other side of the spectrum, to embedded Java. To an outsider, it may appear if time has stopped in the embedded world. The processors are years behind those used in today's desktops and servers, and rather computational resources are often scarce. Now, the weaker the hardware is, the more expensive dynamic compilation becomes. Resource constraints simply don't let dynamic compilers to work in full force. So for embedded world, static Java compilers are Java a ticket. Little known fact that some microsystems before and Oracle now always included static compilers in their Java ME offerings. And somewhere between desktop and embedded world lays a beautiful world of modern mobile devices. Let's now think how JVM can look on a mobile platform. Of course, it needs platform classes, memory manager and GC, reflection, can live without reflection, but I was saying not, JIT compiler. What's missing? The charger. All the modern devices have a battery. So is it worth to spend battery on any application start without reuse it later? Probably it was the reason why Steve Jobs prohibited any dynamic compilation on iOS, and it leaves AOT as the only viable alternative on iOS. So what static compilers exist? At the turn of the century, it was a half of dozen of them, but only 2 have survived. It's Excelsior JET and GCJ. But GCJ wasn't developed several years, so it's finally died this year. But with iOS appearance, we can observe a new Java static compilation development boom. Everyone wants to bring Java to iOS, and you can see several solutions for this. And the most famous until this year was RoboVM. But RoboVM was acquired by Xamarin. Xamarin was acquired by Microsoft. That decided to kill RoboVM. But now we can. But before acquisition, RoboVM was an open source. The core of RoboVM was open source. So now we can observe several forks that would like to resurrect RoboVM from ashes. But now you can use also multi-OS engine that is also a Java static compilation compiler for iOS. And these solutions use Android class libraries. And as you know, that Android also has static compiler called Android Art. And as I said, Oracle always had static compilers in Java ME world. IBM has static compiler for Java C embedded. And our solution covers desktop servers and embedded, and we would like to move to iOS, to mobile world as well. And we believe that we will be compatible solution, unlike those that are use Android class libraries. So let us sum up. And so today you have, and finally, of course, I forgot to say, probably you have heard that finally a HotSpot AOT compiler is going to appear in Java 9 and JEP 295. So Oracle always tried to convince everybody that static Java compilation is not needed, but now it seems they are changing their mind. So let's sum up. So today you have learned that static compilation of Java applications is possible with preserving all Java features, being Java compatible. And it can be useful in many aspects. It can be used for IP protection, tamper resistance, better startup time, predictable latency, and so on, performance, and so on, saving battery. But anyway, JIT and AOT have their own unique advantages. So I believe that the future is for synthesis of these two approaches that I believe will bring the maximum benefits in terms of performance. So thank you very much for attention, your questions, and I have T-shirts for questions, 2 T-shirts.
Thanks a lot for your talk. You've said that Oracle plans to introduce its own AOT feature, and I've tried it on a beta. It seems fine, but from my perspective, there was no benefit for using it. Have you tried the new AOT feature in Java 9, and how it compares with the one that's implemented in your Excelsior JVM?
I have never tried, but I follow, of course, the news about HotSpot AOT. What I see now, yes, first it will be only experimental in Java 9. So, and you can compile, they claim that you be able to compile only Java-based module, but you can try it with other modules as well, but they don't say that it will work for your own modules. And anyway, comparing to our implementation, first, in HotSpot AOT, you will always need original class files to run anyway, because they do recompilation of hot code anyway with JIT. In our implementation, you don't need, in majority cases, you don't need original class files. So one of our selling propositions does not under any worry, because Oracle will not anytime give IP protection feature. As to, but I think that it's good that AOT appears in HotSpot as well, because they only start with it, and of course it's not Google is not perfect in the first version, but I believe that they will evolve it, and someday it will be helpful for developers. Now I don't think that it is helpful, but actually you can try it for startup time, because for warm start type it can improve startup, but for cold startup, they can't improve it because Java base is compiled into 200 megabytes as a shared library. In our implementation, it's only 30. You have T-shirt.
So I downloaded JIT and ran it against JRuby, but unfortunately, I just switched back to a Mac, and so I don't get the one feature I was really interested in, startup optimization. Is there a time frame for that on OS X?
Actually, we have startup time optimization. We don't have now. Yes, it will be in the next version.
All right.
Yes, we forgot to put one, even for startup time optimization for Mac. Now, in the next version, we'll have it.
All right, cool. I'll give it a try on Linux until then. Thanks.
Thank you. Please. Any other questions?
Hi. Have you ever measured how much longer does it take to compile with your compiler compared to traditional compile to bytecode?
Oh, of course, our compiler is a bit slow because it performs global analysis. And yes, it is our not so good point, but we would like to improve it in terms of to introduce smart recompilation, at least, and of course, and we have some other ideas how to improve compile time. But now it is not so good, so you need to wait to compile your application. Yes.
Do you have any order of magnitude? Is it like 10 times slower or 100 times? Or?
Oh, I can't say. We have never measured it. But okay. For 1,000 classes, it can be 2 minutes, for instance.
All right, thanks.
Other questions?
How about garbage collection? Can it somehow benefit from static compilation?
Garbage collection is on the other side because it's a runtime. Of course, we have garbage collector, and it's our own implementation, but it doesn't relate to static compilation at all. It's just a JVM implementation. Many JVM have their own garbage collectors, and of course, we have our own, and we believe it is good garbage collector. It has some advantages in compare with HotSpot garbage collectors as well. Oh, any other questions? So thank you for your attention.